Hey guys, welcome back to AlgoYogi. We are doing graph series and our next problem in the list is Pacific Atlantic water flow. Let's go to LeetCode. This is a really popular problem, so we have to do it. It has to be in the list. There is an M cross N rectangular island that borders both the Pacific Ocean and Atlantic Ocean. The Pacific Ocean touches the island's left and top edges. So basically it's talking about this left edge and top edge of this island. This is the island. And the Atlantic Ocean touches the island's right and bottom edges. So right here, this edge, right edge, and the bottom edge. So this island is surrounded by two oceans. Now the island is partitioned into a grid of square cells. You are given an M cross an integer matrix, heights basically, where height at that particular cell represents the height above the sea level. So the entire island is not going to be the same height, right? So these different values represent the different height of this different places of this island. Now the island receives a lot of rain. It receives a lot of rain. So what happens if an island receives a lot of rain? The water is going to flow out, right? Because it's higher than seas, so the water is going to flow out into both seas. And the rainwater can flow to neighboring cells directly north, south, east, and west. If the neighboring cells height is less than or equal to the current cell's height. Okay, so this is the catch here. Water can flow from any cell adjacent to an ocean into the ocean. Okay, so these cells right here on the borders, the water can flow outside of these cells. Now we need to return a 2D list of grid coordinates. 2D list of grid coordinates result, where result I is basically this coordinate. This is the address of any of these cells, row and column, denotes that rainwater can flow from this particular cell to both ocean, basically Pacific and Atlantic. So now that is our problem. We understood really well. Let's go over it again just to clear things up, and then we'll dive into the brute force approach and our optimized best approach. Okay, so what's really happening here? This is the island. It's surrounded by two oceans. So one is Pacific, this is Pacific. So the upper side and the left side has been surrounded by Pacific Ocean, and the right side and bottom side is surrounded by Atlantic Ocean. So this is the island surrounded by two oceans. Now right here, these values represent different heights of this island from the oceans, right? And we have been told that water can flow out from these cells to the oceans. So water from these cells and these cells can flow out. Basically these cells, the water can flow out to the Pacific Ocean, and then from these cells, there are common cells also, and these cells, it can flow out to the Atlantic Ocean. And what do we need to return? We need to return basically any of these cells from where the water can flow to both Atlantic and Pacific Ocean. So it could be either Pacific this way, or it could be this way or this way. So it has to flow out to basically two oceans, both oceans. And we know that water can only flow in four directions. So vertically, or horizontally. There is no diagonal flow of the water. But what's the condition of water flowing to the ocean? The condition is the water can only flow from one grid to another grid, and then from that grid or the border grids to the ocean, only if the value is smaller than or equal to the neighboring cell. Okay, so let's say if we talk about 5 right here, this cell. Now this cell receives some rain, some water. The water can flow to this grid because this is smaller than or equal to 5. Now from this grid, the water can flow to this grid because this grid is smaller than or equal to 3, and the water can flow to Atlantic Ocean. And from right here, the water can also flow to 4, and from 4 to 2 to Pacific Ocean. So this 5 right here, that's going to be added to our result set. And then that result basically will include this particular address. So basically 0, 1, 2, 3, 4. I should have chosen different colors. So 0, 1, 2, 3, 4, 5, not 5 again, 0, 1, 2, 3, 4. So what's the address of this? The address is 2, 2. So that will be one of the parts of our solution. Our result set is going to include all of these cells from where the water can flow to both the oceans. So right now we were seeing this way, but there might be another cell, or this cell, even this cell, the water could also flow to Pacific on the top and also bottom in Atlantic. That is it. So what is the brute force approach? Let's not make the video too long. What is the brute force approach? We have done a lot of island and graph problems to be able to basically think the solution right here. So what's really happening is, what we can do in brute force, let's write down the brute force approach. Brute force. So in brute force approach, what we can do is, how about we visit every single cell, and on that cell we call DFS, and DFS will take basically the address of this, like let's say R and C, and then it will try to explore all the neighbors, valid neighbors, to this grid, and in the end we can create basically a set. We can create a set that all the neighboring cells it could visit. So let's say from 1 it can't go this way, it can't go this way, but this could also not visit 2, because 2 is actually greater than 1. So water cannot flow from 1 to 2. It can flow from 2 to 1, but not from 1 to 2. So that is why this will basically return 0. So this cannot be added. How about 2? This can also not be added, because water cannot neither flow this way, but water could flow from this point to this way and this way, but it could not flow all the way to Atlantic anywhere, not this way, and not to right or bottom. So that is why it's not going to be in our solution. Well, while exploring this, we have already talked about it. Like, what about 5? Yes, 5 will be able to explore basically Pacific Ocean, and then it will be able to, because it's the edge, it's the border row or border column, sorry. Then it can send the water to Atlantic and also Pacific, and this can definitely, these 4 are definitely going to be part of our solution. Not this one, sorry. This one and this one, these 2 are always going to be part of solution. These are like some observations that you can make. So well, brute force is going to be that solution. You can visit all the cells and then run DFS on them, and then basically try to explore all their neighbors and see if you are able to create a set. That set is going to have values from Pacific side and also Atlantic side. If that's true, then you can add that to your solution. Now let's move on to the better approach. That will be basically using BFS, breadth first search. So now, instead of visiting all the cells and then exploring until you see the ocean, both of the ocean, basically those the border cells, how about we basically start exploring from the ocean? Basically what I'm trying to say is, see, earlier what we were doing is, like, for this 4 to be our answer, we were checking if this 4 can reach ocean. Yes, it can reach Atlantic Ocean. It can also reach Pacific Ocean. Since the water can flow out to the ocean from this cell, the water can also flow in from the ocean, right? Water can also flow into these cells from the ocean. So how about we basically start our BFS with these cells for these 2 different oceans? So what I'm trying to do simply is, we're going to have 2 queues. First is Atlantic Ocean. So these cells are in touch with Atlantic Ocean, and these cells are also in touch with Atlantic Ocean. So I would say that's Atlantic queue right now includes these values. So you could say any of these values. Like, I'm not going to add it, but just let's say this is going to be a queue. Okay, Atlantic queue. Just going to write it. I'm going to change the color. Okay, Atlantic queue. Now this Atlantic queue is going to have all the values that are in touch with Atlantic Ocean. Now we are also going to have Pacific queue. So this queue right here, this queue right here, Pacific queue. So Pacific queue, these are two queues, and these two queues will be holding. So this will be holding all the values right here, and this will be holding all the values right here. Now what we do is we're going to create two sets. So we will be creating two sets. That's our approach right there. So we will have two set, and those set will include the values that we can visit from these two different queues, all the cells in these two different queues. So let's say while visiting all the nodes of Atlantic queue, we're going to create a set. Let's say Atlantic visit, that's the set, and this is going to have all vals, or I mean all cells all cells that can be visited by Atlantic Ocean. Let's just write it like this, right? And one more thing, and then this is going to have basically Pacific queue, Pacific visit set, that is going to include all cell visit by Pacific. Now how are we going to do that? So we will be using BFS. We will append all of these two different queues, and then we will run our BFS. What BFS will be doing, it will be picking these two, will be returning these two different sets, by the way. So this is set one, that is the values that could be visited by, basically by water can enter all the cells from Atlantic Ocean. And then there is this another set, set 2, oh, I can't see it right here, set 2, this is here, set 2, that will include all the cells that will be visited by Pacific. Now then what we are going to do, we're going to return all the common cells that are common in between basically Pacific visit set and Atlantic visit set, and that will be our answer. So let's say for example, let's say we were exploring, using BFS this particular cell as part of Atlantic queue. So what will happen is you can visit, what are the cells you can visit from 4? So you can visit 4, then you can visit 1, then you can visit 3, then you can also visit 2, then you can visit this 2, then you can visit this 3. So these are the cells that you can visit, and you can also visit this 3, and then this 3 can visit this 2. So and also one more thing right here. So what's really happening is these are all the cells that could be visited while you were visiting this particular cell. And at the same time, while you were visiting, what you were doing is you were pushing these into basically you were putting those into the same queue that you're exploring, right? These nodes, you're not exploring them. It's not a DFS, it's a BFS. I'm just showing that you will be basically, while you are visiting 4, so you will be appending this to your Atlantic, but at the same time you will be appending 1, and then next at the same time you will be basically, since it's a BFS, it will all be happening just in single go. That is the beauty of BFS, and that's why it's more efficient, because you have these starting nodes, initial nodes, where the BFS is going to start, and in level by level it will be basically visiting all the nodes that it can, by given the condition that the value that they can visit, it has to be either equal or lesser than the value that my queues hold right now. So this will be our solution. Let's dive deep into writing the code. I think it's a beautiful solution. Most people have written the like efficient code using DFS, but like creating the set and reusing, and then returning these common values is like different people have different style of writing the code. The one I'll be writing, it might look different, but I would say like it's gonna be really nice and clean. All right, so first thing first, we're gonna have our, just like we have our rows and we're gonna have our column basically calculated. So I'll say it will be length heights. So I'm gonna copy this. Length height is my row, number of rows. The number of column is going to be, we can just take first heights. And then if there is one more thing you can do is like if, or we could check, yeah, we can check if not height or not height 0, then we return just empty array, because list is the return type. Okay, so what do we do now? We're going to have, as I said, we're going to have 2 queues. So let's basically create those queues. So first queue is going to be Atlantic. So Atlantic queue. We're gonna have 2 queues. So Atlantic queue is let's use the inbuilt Python queue. So it's called the queue data structure. Then we're gonna have Pacific queue. So queue that is also going to have I didn't copy that. So DQ. All right. So now what we're gonna do is we're gonna fill these queues. How do you fill these queues? So we know that top and bottom. So top is Pacific and bottom is Atlantic. Right is Pacific. Left is Pacific. Right is Atlantic. So what we're gonna do is, like, let's say for R in range, capital R. So this R is going from top to bottom. So it's going row by row. So that means if you go to 0th column, so like this, that will be Pacific Ocean. So Pacific queue, we can append basically R, and because it's Pacific and this is first column we are talking about, so we can have 0, and then at the same time we can add to our alt queue. Alt is like Atlantic queue. We can append, because Atlantic queue is like right side. So right side, the row will be same, but the column will be capital C -1, and that is because of indexing. Indexes start at 0. So that is one thing. We can do the same thing on columns. So let's visit all the columns. C in range column. So if you're visiting columns, so you're basically going, earlier you were going row by row, now you're going to go column by column. So top is basically, if you're going this way, so top is your Pacific. So Pacific will have the value, row is going to be 0, and next is going to be C, and in the bottom is going to be Atlantic, and Atlantic is going to have basically this row is going to be capital R -1, and C is going to be the same, C. Awesome. So now we have both queues filled up. Let's write our inbuilt BFS. So what we can do is, let me write. So I'm going to write this helper function BFS. So it will be BFS. What it's going to take is basically both of these queues. So it's going to take a queue, let's call it queue, and then it will run that BFS on that queue. Before I implement this, what I'll be doing is I'm going to create 2 sets. So as I said, there will be alt set that will contain alt visit set. It will be nicer to call it alt visit. So Atlantic visit set that I will get from my BFS by sending in this queue. Right, this queue, and then I will have Pacific visit set and that I will also get from, oh my god, why am I writing DFS, since I've solved most of the problem using DFS. So BFS, and this BFS will be taking Pacific Q. Pacific Q. Okay, we created some error, and then in the end we can just return the list of, basically you can use a for loop, but this also works if you have basically each of these values present in both of them. So this also works. So what we are really saying is, like, basically we are creating the list of all the values in these two sets that are common. All right, that's the way I learned in Python, and I hopefully it should work. That's the way I have seen it in the code done. Okay, so now we're going to write BFS. That's the most important part of this whole solution. We're going to create a visit set. It's going to be empty in the beginning. Then we are going to visit everything in this queue. Okay, so while queue is not empty, let's pop out R and column from this queue dot pop left. Okay, now this particular it would be one of the cells on the edge of our island. What we can do is, like, we're going to explore its neighbors. So how do we explore its neighbors? So for, let's say, for dr dc in basically we can say I think I can just simply assign it right here instead of calling, like, separately having the directions. So 1 and 0, and then 1 and 0, and then -1 and 0. So basically you are changing the row. Then we can change the column, so 0 and 1, and then we can basically have 0 and -1. Okay, so for DC, so direction row, direction column, we have been doing it forever now. So new row and new column is going to be dr plus our old r, and c plus it's going to be basically dc plus our old c, the current node that we are visiting, or current cell that we are visiting. So right here we get our new address, but we are going to only add this to our queue and to queue and visit set once you basically okay, this is the position where we should be adding this R and C. So this R and C needs to be added to our visit set. So visit, and then we can add it to visit.add R and C. Okay, but now we're going to explore only these. We're going to add these to our queue only when we are basically they are valid. They're not out of bounds, and their values, that neighbor value is basically now greater than or equal to, because we are going from ocean to the land, like I mean land to land, but like from ocean side. So you have to go up. The water can go up from ocean, right? Okay, so if this new row is basically I would say greater than or equal to 0, and this new column is greater than or equals to 0, and new row is basically less than or equals to, not equals to, less than the border, basically R, and this new column is going to be less than our basically column, and this particular new row and new column is not in visit already. You have not visited it, and most important thing is this is not part of I think you can see it. Yeah, you can see it. What if I like press this? I don't know. Okay, so, and most important part is basically in my height at this R and C. So this new r and new column, this value has to be greater than or equals to our currently being visited node or cell. Okay, that is it. If that is the case, then we can append it to my queue. So queue dot append this new row and new column. Okay, and in the end, finally, once you are out of the while loop, then you can return this visit set, this new visit set that we just created, and say while we are visiting this particular this row and current row and column, we can keep adding it to our visit set so that we are not falling into the loop, right? So all the valid node will be visited, and that too, like the water can flow into those cells. So valid cells will be visited. So I keep like exchanging the word node and cell, so they represent the same thing. We are doing the graph problem, so graph concepts, in graph theory you study node, and since it's like an adjacency list, so we can also call it cell. All right, so I think that will be it. Let me zoom out and see if you can see the entire code together. Maybe not, but I'll just scroll through it. Yeah, it was a long solution. Okay, so now let's go over it again. It's been a long solution. So if node heights or node heights 0, so neither row nor column, just return the empty list. Row column, calculate the height, and column, then create two queues, then fill those queues, go over all the rows, then add basically to Pacific Ocean, basically the left side. So row changes, column remains same, column basically column in the end for the Atlantic Ocean, and then you fill basically using the column. So basically top and bottom. So top is Pacific, that's where you adding, keeping the row same, 0 basically on the top, and then in the bottom keeping the last row, and then column changes. That's done. Then you basically create two sets, and this is how you basically return the common values in those sets as list, 2D list. And then these sets were returned by the BFS. In BFS, you basically were visiting each of these, let's say one of the queues, like Atlantic queue, where you were creating like empty visit set. And then while the queue has anything, you keep exploring its neighbors. This is where you explore its neighbors. And for the valid neighbors, you add them to the queue so they can explore further valid neighbors. Okay, so I think that is it. Let's try to test it, and if there is some issue, we will take care of it. dq.append line number 12. What did we do? Yeah, of course, we forgot to add this. Okay, and then here as well. Not to worry, these things happen. It's okay. Awesome. That was the only typo we had, and that is crazy, guys. All right, so that is it. We have submitted our solution. This is very efficient, guys. 20%. We have beaten 20%. I don't care, but we have written like one of the best solutions. Time complexity is going to be big of m cross n, and that is because you are visiting at max all the grids, but basically for both of them, so it could be like twice into m cross n, because you have two queues, and those two queues explore basically the all of the so I would say, like to make it seem more valid, you can write 2 into m cross n, and the same way going to be the space complexity. So because we have two sets, and those two sets can actually have those two sets can have both of all the cells added to both of them. So like work, they were designed in a way, the island was designed in a way the work could flow all the way to all the sites. All right, so that is it. That was a good solution. The video is going to be pretty long, but yeah, I'm happy we solved it. All right, so let's go back to AlgoYogi, mark this problem solved, and see you guys later in the next problem. Until then, bye-bye.